So let me welcome you to this lecture 11 of our course on reinforcement learning at ASU. In the previous lectures, we talked about offline training, which are approximation architectures, neural networks. And we're going to review some of this material. And then we're going to see how these architectures can be used in the context of training and approximate value and policy iteration. And then we're going to look at a different type of parametric architecture, aggregation. And we're going to discuss some of the special issues associated with that. So here's the outline. We first are going to review ideas of offline training parametric architecture that we discussed last time. Then we are going to talk about finite horizon dynamic programming problems and how you train approximations offline to use for value iteration and also for policy iteration in infinite horizon problems. Then we're going to discuss aggregation and a particular type of aggregation called aggregation with representative states. It's a form of discretization, interpolation type of approximation, and it is one of the forms, the basic types of architecture, perhaps the simplest aggregation architecture, and there are more complicated types of aggregation, which I will refer to due to the class notes. So let's go into a review. First, look at a familiar figure involving approximation value space with one step look ahead. At a given state xk, we minimize over qk the sum of two things, the immediate first step cost and the future cost as represented by an approximate cost to go function, k tilde. And we may use also approximatization here, approximate the expected value. We have been focusing on methods to construct cost to go approximations. And last time we looked at the parametric architectures, neural networks, and aggregation also fits that framework here. There is the multi-step look ahead counterpart picture. And we've gone through that. And in reinforcement learning, there are two types of parametric architectures that we use. One is approximating cost functions, like the cost function for policy, or the Q factor of the policy, or the optimal cost function, the optimal Q factor, or approximation of policies, approximation policy space. And the methods are quite similar. There are some more options for approximation policy space based on classification algorithms, but otherwise the methods are relatively similar. And we are going to, in this figure here, consider the case where the target cost function that we want to approximate is a cost function, j sub x. So what we do is we collect training data to generate a number of states, x1 up to xq, a large number of states, corresponding values of the target cost function at these states, perhaps with some error, and we feed them into an algorithm that chooses a function j tilde to approximate this j sub x that depends on a parameter r. And the process by which you generate this function, find r, is the training algorithm. And it can be done with specialized optimization software like gradient type methods, other least squares methods, neural network software, and so on. So we generate the training data and run an optimization algorithm that matches an approximating function from the parametric class to the data. That's a general idea. So more specifically, we select a class of parametric class of functions that depends on the state and also on a parameter vector R, which involves a finite number of parameters that can be tuned And we adjust this vector to change J tilde and to match the training data from the target function. And depending on whether J tilde is linear or nonlinear, or we call the architecture linear or nonlinear. Two major types of architecture are feature-based. Architecture is feature-based if it depends on X via a feature vector, phi of X, that captures major characteristics of X. By this we mean that the functional form of J tilde depends on X through phi. There's another function J hat here that depends on phi, and it's identically equal to J tilde. So the intuitive idea here is that the features can be made to capture the dominant non-linearities in the cost function. So we can afford, in many cases, to use a linear J hat, a linear in phi. And all the non-linearity comes into this perhaps complicated features. And a linear feature-based architecture is an important class because it's relatively easy to train. And it has this form. J tilde of X of R is a linear combination of the features up from 1 up to m, weighted with coefficients R, L, which are tunable. So the vector R consists of the m components which enter in this equation here. And what you see here is the inner product of R and the feature vector phi of X. Phi of X are components of phi. So schematically, a linear feature-based architecture, after it's trained, it for a given state, it extracts features out of the state, this feature vector phi of X, and these features are linearly weighted according to this expression, with the coefficients being the result of the training. So given X and given the results of the training, we obtain in this way a linear cost function approximation of the target function. Now, for feature-based architectures, we need to be able to construct features, problem-specific features. Sometimes these features are not apparent. Oftentimes, they are not apparent. And the nice thing about neural networks is that they construct features for us based on data. And the picture is what you see here for a simple neural network involving only one layer. So given a state, X, it produces an approximation to the cost of that state. And this is done by taking the state encoded in some form that's suitable for the neural network. Perhaps this encoding may involve also some problems with specific features. This encoding y sub x is passed through a linear layer where the matrix A here and the vector B consist of tunable parameters that are the object of training. At the output of the linear layer, we obtain a vector which is passed through a bank of nonlinearities and produces m features at the end, which depend on X and also depend on V. V are the tunable parameters of the linear layer. And these features are weighted with the parameters R, which are part of the parameter vector of neural network, and they give you a cost approximation of the target function of X. So it's a complicated construction. The training problem consists of first collecting a training data, a set of state cost pairs. X of S is the state of the S of component S of the data set. Beta of S is the sample of the corresponding cost at X of S. So we have this training data, And we solve a training problem, which consists of usually a least squares minimization. Beta sub s is the sample cost of the target function. What you see here is the output of the neural network. It involves the coefficients R. It involves the matrix A, involves a matrix B. All of these are tunable parameters that we minimize over. And it involves M features. The feature that comes out of this bank of nonlinearities is this sigma that you see here, and depends on the health component of the output of the linear layer. So this is the linear approximation, and it is matched to the training training data. We solve this minimization problem, and we obtain the parameters A, B, and R of the neural network. Now, this optimization problem is just horrible, absolutely horrible, and it's also very large because it involves potentially a large data set. In other words, this is a large sum of many terms. So conventional optimization methods like the standard gradient method, Newton's method, whatever have you, do not apply very well. And the situation would have been hopeless except for the discovery of these incremental methods that process the data one data point at a time, also called backpropagation methods. It's critical to use some kind of incremental method. And there are many of those, and research is continuing in this area. People work on better methods and were specialized in particular applications and so on. Now, there are two important generic properties here. One is the universal approximation property of neural networks. It states that with large enough size, with large enough layers here, linear layer, we can approximate anything that might be of interest in practice. Any target function can be approximated with large enough layer here. We just only one layer. We don't need many layers. Just one is sufficient. This property has been known for a long time, 40 years, perhaps even more. A more recent important structural property that has been discovered is that deep neural networks, networks that involve many layers, not just one, but many layers, they have some important advantages. And recent research has linked the advantage of deep neural networks to over-parameterization. Many ways more than the data points. So that's what we call over-parameterization. And it turns out that over-parameterization helps both in providing parameters that match the data set well, but also parameters that work well for outside the data set. So they have a good generalization properties, as people say in this field. There's interesting theory that's associated with this parameterization idea, and there's a lot of research that has been done in the last 5 to 10 years in this area. So that's, in a nutshell, is a summary of what we did in the previous lecture. And now we want to see how these architects work in the context of the critical problems in approximate dynamic programming. So we'll look first at finite horizon problems, and we'll try to approximate the dynamic programming algorithm, the n-step dynamic programming algorithm, sequentially starting from the end and going backwards, and with each step providing an approximation, neural network approximation or otherwise. Okay, this is also called fitted value iteration. That's the name that you'll find in the literature. It is a sequential approximation going backwards starting from the last stage and going to the first stage. So we train cost approximations, J tilde n, J tilde n minus 1, up to J tilde 0 in place of the optimal cost functions, Jn star, Jn minus 1 star, J0 star, which is the optimal cost function of the problem. And we do this sequentially going backwards, similar to the dynamic programming algorithm. At every step, we do an approximation. So we start with J tilde n equals to the terminal cost. Gn is a terminal cost function. And given the approximation at step k plus 1, we use one step look ahead to construct a large number of data pairs, state cost pairs, XKS and beta KS, where beta KS is the right-hand side of the dynamic programming algorithm with the approximation J tilde in place of J star. So we pick somehow 100, 1,000, 1,000,000 or more data points, states, properly balanced and distributed within the state space. For each one, we do this calculation here, and we form this data set. And that gives us the training set by which we train an architecture, J tilde parametric architecture, J tildes of K. Given J tildes of K, we do the similar thing here, obtain data and train J tilde K minus 1, J tilde K minus 2, and go backwards all the way to J tilde 0. Now, there's something that's unpleasant here. And that's the following. Every sample, every one of these betas that you calculate involves minimization of an expected value, okay? Exact minimization of an expected value. Now that can be a pretty formidable calculation. The expected value can be a substantial calculation, and you have to do it for every control. All of this just to obtain a single data point. So this can be a substantial calculation. Of course, it's not as the situation is better if you have a deterministic problem, so there's no expected value here. And if you have relatively few controls, as opposed to a large number. So in any case, suppose that we have calculated a data set, then what we do is we minimize over the parameter of the target function. Perhaps some regularization term might be added here. And typically we use an incremental method to solve this optimization problem. Now, there is an advantage here. After you have trained these cost approximations, then what you use in online play is exactly the same minimization as here. So essentially the software that you use for training is the same as the software that you use for online play. In this way, the Newton step interpretation applies. So we gain the kick in performance out of the Newton step. On the other hand, the problem is what I mentioned earlier, a difficulty that minimization of expected value complicates the collection of samples, makes the information data set more difficult. Okay, now here's another way to implement the same idea, fitted value iteration going backwards, but instead of using costs, we're going to use Q factors. We're going to fit Q factors, approximate Q factors. So how do we do that? We introduce a parametric architecture involving Q factors. Q factors depend on both states and controls, and also here's the parameter. And we remember from finite horizon dynamic programming that we can do the algorithm in terms of optimal costs and also in terms of optimal Q factors. And the algorithm in terms of optimal Q factors looks something like this, except that there's Q star here and Q star here, okay? And if we want to do backwards approximation, parametric approximation, That's the kind of approximation that we have to do at every step. Given q tilde k plus 1, we want to match q tilde k to data that comes from this calculation here. So we obtain q tilde xk, uk, rk for many triplets, xk, uk, and beta k, where beta k is a sample of this expected value, okay? Now, sample, the word sample is important here. We don't need to calculate the exact expected value, which might take a lot of calculation. Just samples of this is sufficient. This is a mathematical magic trick. The order, relative to the algorithm of the previous slide, the order of expectation and minimization has been reversed. Whereas before you had minimization of expected value, here we have expected value of minimization. Minimization of expected value cannot be approximated. However, expected value of minimization can be approximated by just a few samples. So we don't have to calculate the full expected value here to form this beta case of S. It's sufficient to take 1 sample, 5 samples, 50 samples, and that's just fine. You throw it into the same least squares optimization, and it works. That's the nature of the mathematics here. Okay. Are there any questions about this fact, this trick here? And why we can use just a few sample approximation of this expected value as opposed to a full expectation? Okay, there's another advantage to this. Methodology based on Q factors. The samples of this, the samples of random samples here, can be obtained in model-free fashion. We don't need to have the mathematical form, a closed form expression for the cost. We don't need to have a model, a mathematical model of probabilities. A computer model is needed. Of course, some model is needed, otherwise we go nowhere. But the main difference is that we don't have to have a mathematical model. It's sufficient to have a computer model. That's what model-free means. Doesn't mean that you don't have to worry about modeling at all. You've got to have a computer, and the computer, the simulator, can generate samples of this form. For a given xk and uk, you can generate a random sample of the first stage cost and a corresponding sample of the next stage. So what you need is a black box. You feed it x and u, and out comes g and xk plus 1. You don't need to have formulas for probability distributions or whatever else. So that's another nice thing about this approach. Now, having collected this data set, having done the training through least squares or whatever, with incremental methods, whatever, what have you, then we can obtain the one-step look-ahead control online in this way, without the need of a model or expected value calculations. We have trained Q factors, we minimize over all Q factors at stage xk, and we obtain the control to apply after the training is finished, and we have this RK. That's an important advantage. The online calculation of the control is simplified. We have a neural network or other approximation architecture. We feed it the current state, and it spits out all the various Q factors, and we minimize, perhaps by brute force, minimize over these Q factors. On the other hand, if you have approximated Q factors, the Newton step property is lost. You don't have you don't do the proper minimization that involves the cost, the expected value, and so on. Also, after you train with some problem data, if the problem data changes on you, as in adaptive control, for example, then you need to do online replanning. But when it comes to online replanning, this is a bad thing to minimize because it has been trained on a specific model, a specific set of parameters. Once we change the parameters, then this can be very bad. You're using controls with approximations for which do not match the model, the current model. So how one can address these issues? Well, with more work. And this work involves approximation in value space, involving the cost and the probability distributions, either provided by a mathematical model or by a computer model. So you use approximation in value space, and you calculate a J tilde here using this minimization. You can do it with training, extra training, to extract a J tilde out of this Q tilde, or you can do it online if the number of composed is relatively small. So in this way, the Newton step property is recovered, and also the algorithm is resilient to online replanning. For model changes, you still use the simulator to calculate the correct cost function and transition probabilities. Okay, so these are important issues in using the results of training dynamic programming. Have any questions here? This is an important slide, and I urge you to try to understand it. It's also explained in the class notes. Okay, now here's another issue in training. Should we approximate Q factors or Q factor differences? Differences involving different controls. Now we have touched upon this issue when we talked about variance reduction. You remember we had some discussion about variance reduction. We said that we need to focus on Q factor differences and target our variance reduction to the Q factor differences. So now we're going to look at this issue in a little different context. Okay, suppose we approximate Q factors. Here's an example of bad things that can happen. Suppose that you have a scalar system and cost per stage of this form. Xk plus 1 is just xk plus delta uk. And delta is some positive number, it's very small. Think of discretization of a continuous time problem involving the simple differential equation. X dot equals u, okay? If you discretize this equation, standard discretization, you have this equation here, this discrete time approximation, where delta is the discretization interval. So ordinarily, you want to make delta very small. The corresponding cost per stage from t to t plus delta is something that's proportional to delta, and it's quadratic. I'm taking this example to be quadratic, okay? So this is a problem that's very commonly, this is an instance of a class of problems that's very common in practice. Have a continuous time problem, you discretize it, and if you want to faithfully discretize, you have to take delta very small. And this is a linear quadratic problem, also can be solved in closed form. So let's consider a linear policy. The policy applies at x, it applies minus 2 of x, just an example. Its cost function can be calculated with Riccati equations, with the standard formulas that we have gone through. And if you do this calculation, that's what you get. Okay. Now look at this formula here. This is an exact form of J mu for this mu. It is quadratic in x, as you expect. In linear quadratic problems, the cost functions of linear policies are quadratic. And if you look at how delta enters this equation, there's a term that doesn't depend on delta. There's a term that depends linearly on delta. And there's a term that, and some other terms that depend quadratically on delta. So for delta small, this term doesn't count here. So this is the cost of a policy approximately as a function of delta. Now, if you compare it to the cost per stage, it is huge, okay? Because this does not involve delta, it's the dominant part. However, this one is proportional to delta. So when you do approximation when you construct Q factors, the Q factors involve the sum of J and U and the sum of the first stage cost. And the corresponding Q factor, you can calculate it to be like so. Okay, we add here the quadratic term that corresponds to U squared multiplied with delta. So the Q factor involves a huge term here, a little delta term here that involves X and U, and also an O delta squared term that doesn't count much. So the Q factor involves the sum of disproportionate terms. And the important part here is the part that depends on U. That's what we minimize. However, this part here, which is the important part in this formula, is washed out in magnitude by this term here. So the important part for policy improvement is this. That's the only thing that involves U. On the other hand, if you approximate this with some Q tilde, the approximation is going to try to catch this term here. And this is going to be in the noise. It's going to disappear. So you're going to get nonsense when you try to approximate this thing here, because this term that dominates is irrelevant to what you want to do. On the other hand, if you approximate the Q factor differences between U and U prime, this term here is subtracted away. So you're approximating the right thing, the important thing. And the problem of disproportionate terms does not arise. So you will see a lot of literature about what people call advantage updating, or the use of baselines where you subtract out some dominant terms in order to make the training a little better. This example is representative of the difficulty in this context. Are there any questions about this example? Okay, so let me pose this problem in a little bit more general context. As I said, there's a lot of literature in this area and a lot of art getting this, okay, doing this Q factor difference approximation is not easy. So this represents a more general issue, disproportional terms in the Q factor calculation. And the remedy, generally speaking, is to subtract state-dependent constants from the Q factors, which we find the term baselines in the literature. The use of baselines is also arises in machine learning in general, when you're trying to fit functions to data. And the constants subtracted should affect the offending terms, cancel them out in some sense, at least partially. So let me give an example here. Suppose you consider truncated rollout with a policy view and some terminal cost function approximation. So when you, so the cost function approximation is, roughly speaking, close to the cost of the policy view. And in approximation in value space, we minimize over U this expression. And the question is how to deal with a problem where G is tiny relative to J tilde. Okay. In truncated rollout, there are approximations, and if this is tiny, it's going to be lost in the shuffle. And when is this G tiny relative to J tilde? Well, we saw one example of that when we time discretize continuous time systems. Okay, that was what happened the previous time. But another case is when there are sparse costs, or sometimes they call it sparse rewards. In other words, most of the cost is incurred at the end of the horizon. And in the meantime, the costs are zero or very small. Now, the intermediate costs are these G's. If this is zero, then everything depends on J tilde. And if you don't properly approximate J tilde, you're going to be in big trouble. G is insignificant. So one remedy here is to subtract a baseline from J tilde and train using the difference. And for example, J tilde of X. And this is J tilde at the next state. So we train with cost difference between current state and next state, as opposed to training with the cost of the next state. All of this I'm going through very fast. It's an art, and there's also a lot of special cases discussion that goes into this. And there is discussion in your class notes. What can we do in situations like that? One possibility is, instead of learning J mu's of X, learn the difference between J mu's of X minus J mu at X prime, because that's what's important. And in this way, we introduce automatically some kind of baseline. And this is known differential training. Training on cost differences as opposed to training on costs. Another methodology is advantage updating, where we work with relative Q factors and subtract the state-dependent baseline, which is the minimum Q factor, from the ordinary Q factor. So we approximate advantages, Q factor differences, as opposed to Q factors themselves. A lot of art that's involved here, and I just want to sensitize you to the issue. I urge you to look more closely into the notes and other literature. Okay, so this is for finite horizon. A lot of things that hold for finite horizon extend to the infinite horizon case. But also in infinite horizon, we have the important method of approximate policy iteration. Policy iteration is primarily for infinite horizon problems. So we want to look at the use of trained approximations in the context of policy iteration. Are there any questions? Okay, let's do some review. Let's look at the exact policy iteration, which we never really studied in depth, but we have touched upon at several places in our course, including at alpha zero, when we discussed alpha zero in the very beginning. When it comes to computations with policy iteration, we prefer to use finite state transition probability notation, because ordinarily the system involves a finite state space. And the policy iteration consists of two steps. Every iteration involves a policy evaluation phase, where we compute the cost function of the current policy and also its Q factors, okay, the expected cost of the first stage plus the expected cost to go over policy. We're talking about exact policy iteration here. And policy evaluation gives the Q factor, this expression here, and then we obtain the new policy by minimizing at every state the Q factor, obtain a control at every state. That's a new policy. So this is exact, and it has theoretical properties that are nice for discounted problems, discounted finite state problems. For problems other than discounted finite state, there's quite a bit of trickery involved in this policy iteration, and there's a lot of theory that goes in it, but in reinforcement learning, people take it as for granted that policy iteration is a solid algorithm in exact form. It's not, but okay, people think that's exact. It is reliable. It is reliable for discounted problems, but not for other problems. Okay, now let's see what happens when we use approximations in policy iteration. The policy evaluation is approximate. We cannot compute these Q factors here, so we approximate with a parametric architecture. And then we determine the parameter of the architecture in the usual way by generating a large number of training triplets, states, controls, and Q-factor samples. Okay? And we fit the Q-factor samples to the samples provided by the architecture to the least squares fit and determine the parameter R by minimizing this least squares problem with incremental gradient methods, with the usual backpropagation stuff. So that's the approximate policy evaluation. Gives us an approximate Q factor in place of its exact or the exact. And we calculate the new policy with policy improvement in the standard way. We minimize the approximate Q factor in place of the exact Q factor. Okay, so that's the approximation scheme. Now let's look at some practical issues associated with that. The first thing I want to warn you about is that there are big challenges here. If you think that approximate policy iteration can be made to work quickly and reliably, sit down and within a week you have it all working, don't count on it, okay? We have looked at rollout. It's a piece of cake by comparison. There are big challenges to make approximate policy iteration work. If you read the literature, they say we use approximate policy iteration, here's the result. They don't tell you how much they struggle. And they don't tell you also how representative the results that they give are. They tell you about the successes after a lot of tweaking and tuning a specific problem, but they don't tell you about the failures, okay? Be aware of this. So what are these big challenges? There are a number of them. Okay, issues of selecting architectures, approximation architectures. You would like to use a linear feature-based architecture because the training problem is simpler in this case. On the other hand, you have to have good problem-specific features. And for a given problem, this may not be easy to come by. You may get some features, but not a good enough set of features to trust training with a linear feature-based architecture. So if you don't have good features, then you have to use something like a neural network, but then the training issues are harder. Moreover, there's a generic difficulty here. If you have a problem with changing system parameters, an adaptive control type of problem, then you'll need online replanning. But online replanning means starting again from scratch with a perhaps different architecture and with the offline training for a different set of parameters being more or less useless for a new set of parameters. In other words, the training is targeted to a specific model of the system. The model of the system changes, so does your effort that you did for training. So these are the architectural issues. Okay, there's an important issue around exploration. Exploration has to do with how you generate the training set in order to get good approximations. So you have to explore the state space enough to get a representative training set. But there's some fundamental difficulties here. Remember, policy iteration involves policy evaluation followed by policy improvement. Now, given a policy, to evaluate it, you have to simulate it. Let the system run using this policy. So the samples of J mu's of X are obtained starting from states X that are frequently visited by mu. In other words, this policy view may have a tendency to go on this side of the state space. Well, the samples are going to come from that side of the state space, but not from other sides of the state space. So what may happen is that we may have some represented states, the states favored by the policy that you train with, in some other states which are not represented. And then when you go into policy improvement, this may create serious problems. The underrepresented states, which are unlikely to occur until you, will throw off the policy improvement. Because it may be that the next policy wants to go into another part of the state space, but if you don't have good approximations within this part of the state space, you may get nonsense, essentially. This is killer difficult, okay? Can really, it's very hard to deal with. There's a lot of literature on how you generate a representative data set. There are remedies, none of them perfect. One possibility, instead of using long trajectories and generating lots of samples independently, simultaneously with a given policy, you use short trajectories, but use more initial conditions. So more initial states to sample the state space in a more representative way. Another possibility is, in addition to sampling with a current policy to evaluate it, you sample with a so-called off policy, a policy that's under the new, so that it tends to steer you and collect samples from different parts of the state space. Okay, this is an old idea. There's a lot of flaky stuff that has been written about off policies. Making an off policy work is difficult. Don't let anyone tell you that we'll use an off policy or an epsilon optimal policy or things like that. Doesn't work always, and it may work only with problem-specific tuning as opposed to generically. There's no guarantees that this is going to work. There are also other ideas here, and I can refer you to literature. You can look at your class notes and so on. So people have worked a lot on exploration issues. Some people have worked with instead of getting a data set involving states that have been generated not only with a current policy, but also with previous policies. This is called a experience recall buffer, okay? A buffer, you build a buffer of initial states that involves multiple policies. And okay, there's a lot of magic, voodoo, and luck involved on all this, okay? A third issue that is not quite understood, in principle is devastating, but in practice, somehow things work out. It has to do with oscillations. Exact policy iteration generates a sequence of policies that converges. At some point, it terminates with an optimal policy. Approximate policy iteration generates a sequence of policies that in the beginning, they tend to improve the cost, but then after a while, they tend to oscillate. Sometimes they improve, sometimes they deteriorate. And the oscillation can be, in examples at least, can be quite wide, way far from the optimum. And this is not a problem that happens occasionally through bad luck, so to speak. It's a generic problem, okay? A generic problem, and you can understand it even with the concept of simple examples. There's even more to this that's even more weird. There's a phenomenon called chattering, which I'm not going to explain here, but you can look at the literature and you can see, you can understand it because it occurs even in very simple examples. Remember that here we are approximating policies that are parameterized. So the parameters of the policies may converge to something. You can see them converging, but the corresponding policies are oscillating. Now, how can this happen? The limit of the parameters may correspond to multiple policies, and the method oscillates between these policies. And the oscillation may also occur far away from the optimum. It's really devastating examples. However, it turns out that these occur in small problems primarily. For large problems, they tend not to occur through a mechanism that I cannot explain. So that's why people are not complaining much about oscillation issues. They are there, they can be seen, but they are not devastating in practice. Another thing that I want to mention about oscillation is that they do not arise in specific approximation contexts like in aggregation. I'm going to talk about aggregation shortly, and aggregation does not suffer from this difficulty. It suffers from this difficulty, but not from this difficulty here. So that's all I have to say about approximate policy iteration. And this slide is supposed to warn you that not all is rosy within this area. Are there any questions?
So why do policies repeat in cycles when you have some sort of when the parameter space is just more or less the same when you converge? Like, that doesn't intuitively, it feels like you should have only a small one or two policies that work in a converged space optimally. But if are you saying that there are multiple policies that would all result in the unequivalent quality of control? Or
yeah, the question is, why does this occur, particularly small problems? And you're right. You may have parameters for which there are two policies attaining the minimum. And the method jumps from one to the other. And these policies can be very different and have highly non-optimal costs, okay? So that's the mathematical context, how they arise. Now, why you actually tend to be attracted to this kind of singular points, that's something that I cannot explain here, but it's easy to understand if you look at graphical interpretation, what happens even in two-dimensional space, for example, two parameters. In parameter space, suppose there are two parameters, and you can see that, okay, this cycles, the optimum may be somewhere down here, but the method may get caught in some kind of a cycle far away. And okay, you have to have a picture to understand that. But that's what's happening.
okay. I'm imagining something like the butterfly attractor, where you have 2 points and it has chaotic behavior. Is that sort of what's going on?
Chaotic behavior, it is chaotic, but I can't connect it to a particular example.
Okay.
It's pretty chaotic, yeah. Behavior, particularly when it involves sampling, okay? Because probably if the sample is deterministic, then there's not much chaos. But when the problem is stochastic, then there's a lot of chaos. Okay, so let's take a 10-minute break. And we're going to aggregation. Get back at 5:40. Okay, guys, we're going to get started. So we're going to talk about a relatively new topic, aggregation. And it arises in the context of offline training. Coming back to our basic picture, notice here that I've changed notation a little bit. We're going to be talking about an infinite horizon context. where we're going to be using I and J for states and the transition probabilities instead of system equations. However, it's the same concept, minimizing at a given state I, minimizing the sum of the first step cost and the cost of the future stages as represented by a cost function approximation J tilde. And that's where aggregation fits. It is a method for calculating J tildes. And you can view it also as a form of problem approximation. Basically, we have our dynamic programming problem, which is difficult, and we approximate it with a smaller or easier version, which we can solve optimally to obtain J tilde out of that. It's also related to feature-based parametric approximation. Oftentimes, in major types of aggregation, J tilde is piecewise constant. So it's an approximation that's piecewise constant. And you can view this as a feature-based parametric approximation, where the features are 0, 1 set membership functions. Okay, 1 for a particular set, and 0 elsewhere, and so on. We went through an example of a piecewise constant parametric architecture, and this is type of approximation that comes out of aggregation frameworks often. And there are several versions, finite horizon. We're going to be talking about infinite horizon, one step ahead. But there are several versions of aggregation for finite horizon, multi-step ahead, multi-agent, distributed versions, and so on. And also, okay, it can be combined also with other types of parametric architectures, like a neural network, in a couple of ways that I'm not going to go into in any detail, but in your class notes, you can see how it can be combined with a neural network providing features, for example, to use within the aggregation framework. So now I'm going to give you an example that you have seen in one way or another in various contexts. You have a computation that involves states, many states, and this black crossing points. And you want to approximate with a computation that involves fewer states, like having a fine grid of points approximated with a coarser grid of points, these red points here. And the idea is you introduce these red points, which are states. They're sort of representative to form a coarse grid. And then you approximate the original dynamic programming problem with a dynamic programming problem defined on the red states, the coarse grid, a smaller problem. And we call this the aggregate problem. Now, to do this, we need to have transition probabilities from red states to other red states, right? And we need to have costs associated with the red states. So how do we get those from the original problem? That's one issue. But once we have defined this aggregate problem, we can solve it by exact dynamic programming because it's smaller. Say the original problem may involve billions of states. If we approximate this with 1,000 states, okay, may be solvable by exact calculation. And then after you have solved the small problem, the aggregate problem, you extend the optimal cost function of the aggregate problem to the original fine grid. So you get numbers of the red states, and then you make an interpolation to obtain cost numbers on the black states. One possibility is to use some kind of a nearest neighbor heuristic. Like, for example, you have obtained the cost function of the problem on the red states, okay, an approximate cost function. If you want to calculate the cost function at some other black point here, not a red state, then you look at the red state that's closest, and you take the value, the cost value associated with that red state. That's what I mean by a nearest neighbor type of interpolation or approximation. So this type of approximation occurs in various types of numerical analysis, computation, machine learning, all sorts of state contexts. It's a very old type of methodology, and it has been researched extensively. However, dynamic programming poses some special issues that I'm going to go into here. So I'm going to talk about a more general type of a generalization of this preceding example involving representative states, and you can view this as a form of discretization through interpolation. Your class notes there are other more general types of aggregation. I'm going to touch upon those, but we're not going to discuss it in detail. So we're going into this scheme involving the representative states. And in this schematic, you see the states. There are both these red circles and also these black circles. The representative states is a subset of the original state space, which I assume to have n states. So the original states, the black states, are numbered 1 to n. And the representative ones are these red circles here. And we denote them by X and Y, okay? So X and Y are the states and next states in the that are representative, but the transitions of the original problem can take you from a red state to a black state, okay? So the question is, we want to generate transition, we want to define transition probabilities from red states to red states. And the question is, how do we do that? From a red state, I can go to a black state according to the corresponding transition probabilities. But then to get to the red states, I need additional transitions, artificial transitions that are needed to define my problem. And these artificial transition probabilities are called the aggregation probabilities. They relate original states J to representative states, which are red. And these are arbitrary. You define those, and you have, in this way, transition probabilities from red states to red states. So transition probability from X to Y2, for example, is the product of this transition probability times this transition probability. So that's where we're going. So we relate the original system states to the representative states with these aggregation probabilities. You can view them as interpolation weights, if you wish. And however, they are probabilities. For a given J, they are all non-negative and they add to 1. So think of this from J1, you can go to Y1 with some probability, Y2 with another probability, and Y3 with another, still another probability, and similarly. And these aggregation probabilities, you can view them as interpolation coefficients that express similarity or proximity of the original states, the black states, the representative states. Now, once you have introduced these aggregation probabilities, then the aggregate problem dynamics. In other words, the transition probabilities between the representative state X and Y is given by this simple formula. We multiply the transition probability from X to J with the aggregation probability from J to Y, and we add overall J. And this is the total probability theorem, okay? Standard probabilistic calculation. So given phi, this defines the dynamics, the transition probabilities of the aggregate problem. We still need to have the expected cost for the aggregate problem. And what is the expected cost at the representative state X under control U? Well, it's precisely the cost of the average cost of the original problem. when you are at X and you apply U, this is the expected cost that you obtain, whether you are in the original problem or in the aggregate problem. Okay, so that's the basic construction. It's very simple. We simplify the state space, take only a finite number of them, and define dynamics, transition probabilities between the representative states and the corresponding cost using these aggregation probabilities. Every choice of aggregation probabilities gives you a different type of approximation. Okay? And there is an art also in selecting these aggregation probabilities. It's a new concept, a different concept than the neural network cost function approximation. Entirely different idea, but aims at the same objective, creating cost function approximation. Okay, so here's a schematic. We have the original problems that for I to J is governed by transition probabilities under control of U with corresponding cost. And the aggregate problem involves this bottom part and involves transition probabilities from X to U, from X to Y corresponding to U, using the formula I gave in the previous slide, and also the cost given at the previous slide. So for this representative state setting, the aggregate problem is very simple to understand. It takes place even though it goes through the I and J states, you can view it in a simplified way as taking place between states X and Y. Now, after you solve this problem, let's call R stars of X the optimal cost of representative state X. Then you approximate the optimal cost function of the original problem by interpolation using this aggregation probabilities. So J stars of J is the optimal cost function. J tilde is obtained after you solve the aggregate problem, obtain these R stars, and then interpolating between. And as I said, for different aggregation probabilities, you get different kinds of approximation. And an interesting type of aggregation is called hard aggregation. In hard aggregation, for every J and Y phi, the aggregation probability is either 0 or 1. So for a given aggregate, for a given original system state, there's only one aggregate state that we can go to. And as a result, if you look at this formula, J tilde is piecewise constant. J tilde is constant on each set of this form. It's constant on the set of original system states that correspond to a state Y. This is called the footprint set of Y. Let me give you a schematic of that hard aggregation. Okay. So on this axis, you have a schematic states J of the original problem. And these points here correspond to the representative states, correspond to a discretization, so to speak. And for each aggregate state, there's a corresponding footprint. It is the set of all J of which the aggregation probability is 1. Okay. So these aggregation probabilities in the hard aggregation case provide a partition of the state space into these footprint sets. And within each footprint set, the approximation is constant because of the formula that we have here for approximating for J tilde. Only one of these phi's is 1, and all the others are 0. So it's piecewise constant. So that's the easiest example to understand. And it relates to a lot of experience that we have from many other contexts. And this type of approximation, hard aggregation case, provides some insight as to how we should select the aggregation probabilities. Clearly, if the original function, this green function, the target function, J star, is piecewise linear, we want to approximate the green function with a red function that aligns along the corresponding piecewise linear sets. So basically, the idea is that we should be choosing the aggregation probabilities so that the green function does not change very much within a footprint set. And indeed, there's an error bound here that says that the difference between the approximate cost and the true optimal cost is small if J star varies little within the footprint sets. So we have to sort of find where the cost function is sort of flat and then align the partition along the points where you have the corresponding changes. Okay, I'm not going to give a proof of this, and there's a lot more than I'm describing here. I'm trying to cover in just a few slides the main ideas and then point you to the class notes and beyond. Okay, so now suppose that we have defined the aggregate problem. We have this representative states, we have defined aggregation probabilities and so on. How do we solve it? Well, the aggregate problem is just an ordinary dynamic programming problem involving this transition probabilities and this average cost. So we just solve it with any method that you want, an exact method, for example, such as value iteration, policy iteration, instinct policy iteration, any method that can be used, any exact method that can be used for infinite dynamic programming can be used to solve the aggregate problem. Once you solve the aggregate problem and you obtain these R star quantities, then this is the approximation that you get. So that's straightforward. However, it requires exact solution of the aggregate problem. Sometimes the aggregate problem itself is difficult, or it may not have, you may have a model-free situation. You may have a computer model in place of a mathematical model. Then you can use simulation for solving this aggregate problem by combining a simulator for the original problem, combining it with this probabilistic mechanism. So any method, any model-free method that you know can be used to solve the aggregate problem, provided there's a simulator for the original problem. And the model-free method should be exact to get this R star scalars. So this is fairly simple to understand. However, once you get into more complicated aggregation models, it becomes more intricate, but I'm not going to go into that. Are there any questions here? Yeah.
Maybe I missed this, but what is the property that we are looking for to select these representative states?
Look at the regions where the target function is flat. So it's already almost piecewise linear. And then you align the partition within the flat parts. How do you do that? There are techniques for doing it, but the idea is that you choose the aggregate states, the representative states, so that are sort of in the middle of flat areas of the target function. Is that?
I'm trying to think of it from the perspective of state space that is explored or is left or is yet to be explored by the model or the agent that we are using. The target function would only be available for the region of the state space that we know of, right?
What you're really asking is, how do you know which parts of the state space have a flat cost function, have a flat target function.
In one way, yes, yes.
Okay. For this, you have to use intuition of some form, but also you may want to have a preliminary training calculation to identify these areas through a neural network. Now that's far more complicated, okay? But it's possible to follow an approach like that. Use a neural network to construct features of the state for the target function, and then use those features, and consider areas where have similar features, and use these as the sets of the partition. So use the features provided by a neural network to partition the state space in a way that's conducive to aggregation. Okay, I'm going a little fast here. Because we have 2 slides to cover. Okay, the example I gave for representative features and the assumption was there's a finite number of original system states. What if you have a continuous state space? Like you do, for example, in many control problems. Let's assume here that you have still a discounted problem with bounded cost per stage, so that theory is favorable. Now, in that case, you have a continuous state space, but you still take a finite number of aggregate of representative states. It's a discretization. So the representative states approach applies with no modification. However, the number of representative states should be finite in order to be able to do all these reinforcement learning checks and computations, exact dynamic programming computations, and so on. You can still use model-free simulation-based approach for the aggregate problem, the spirit of the previous slide. And in this way, we can obtain a general discretization method for continuous spaces discounted problems. Discretize essentially by using aggregation and solve the aggregate problem. Now, this can be done fairly straightforwardly for discounted problems. But when it comes to other types of problems, continuous state space, like stochastic shortest path problems, mathematically, there are a lot of complications that occur. And I'm just mentioning to you that there are some pitfalls. Not everything extends straightforward. Now, an important context of this continuous state space is POM-DP. In POM-DP, one way to formulate POM-DP to convert them to a perfect state information problem is by using a belief state formulation. Reformulate the POM-DP in belief space, and then the belief is a state, but it's continuous, right? So how do we deal with that? Well, you just use this representative states approach. It still applies. You just apply it within the belief formulation of the POM-DP. And then the aggregate version of based on representative states, the aggregate version of the POM-DP problem is a finite state MDP. Okay, it can be solved with standard discounted finite state problems, the algorithms, and it can be solved for the cost vector, and then by using any kind of model-based or model-free methods, such as value iteration, policy iteration, so on. So you have this POM-DP in belief space, then you discretize it by using the representative states, and then you apply your favorite method, exact dynamic programming method for discounted problems. And then after you obtain the optimal aggregate cost vector, you obtain an approximate cost function from the POM-DP by using interpolation. And this J tilde defines an approximate cost function that can be used for one step or multi-step look ahead in an approximation in value space. That's a very viable approach for POM-DP. POM-DP has an infinite belief space, discretize it using aggregation, and you can solve it with standard MDP methods. Note that for POM-DP, the control space is still finite, okay? So you don't have to deal with discretization of the control space. Now here's a situation where you have to discretize a control space. Let me give you an example. Here we have a problem that involves both a continuous state space and a continuous control space. It involves continuous motion. You have a self-driving car that wants to drive from point A to point B, perhaps through obstacles, and has to choose the trajectory in state space and also the control in continuous space. The control is the direction along which you steer the car. And we assume here that we want to drive from A to B. And okay, it's 1,000 meters, 1,000 meters, and the travel speed is 1 meter per second in any direction. So now let's follow an approach that comes to mind immediately. We just discretize the continuous state space into a grid, okay? And then we say, we're going to solve the problem on the grid. And we can go up or down or sideways and go from A to B. So we restrict the directions of motion to horizontal or vertical. And then we solve this discretized problem in place of the original. Is this a good approximation? What do you think? Many people would say, yes, a good approximation. I've heard some very reputable people in the field say, yes, it's obvious. But is it true? Why don't you take 2 or 3 minutes to think about it? There's something wrong with using this approximation in place of the optimal in continuous space. Any comments?
It's entirely possible that the discretized state space can result in paths that are just not feasible. So, for example, if you
Can it result in what?
it's possible that something that is feasible in the continuous space is not feasible in the discrete space. So, for example, if you have 2 large objects with a narrow gap in between them, if you have and the optimal path only goes through this gap.
Yeah, what you say is that the discretization may not be consistent with the obstacles that we have here.
Right.
I agree with that, but suppose there are no obstacles at all. So this issue does not arise. Okay, go ahead.
Yes, since we are discretizing it, so the distance traveled will be along the horizontal or vertical, so we will be traveling more distance instead of traveling the shortest path. So the finer the grid, the better approximation.
Yeah, what you're saying is that by restricting yourself going up and down, you may have to travel more distance, may not be able to approach the optimal distance.
It's actually,
yeah.
in this case, it's the same distance because it's always the Manhattan distance between the 2 points.
Okay, yeah. So in this way, it's the Manhattan distance, which is 2,000 meters. Okay. However, the straight line, which is the optimal, is only square root of 1,000 meters. So there's always a gap between the discretized solution, no matter how fine the discretization is. You may discretize with a zillion points, but still, it's because you're restricted to go in the 4 directions, you're going to be traveling 2,000 meters total. Whereas here, you can go with a square root of it. 1,000, which is less. Okay, I think you got it. Okay, so I'm reiterating what you stated. The discretization is flawed. Okay, so assume all motion was 1 per meter and no obstacles. Then the continuous optimal solution is a straight line from A to B, again ignoring obstacles, and has length square root of 2 kilometers. The discrete optimal solution has length of 2 kilometers, regardless of how fine the discretization is. Now I'm assuming that each motion, right, left, up, and down, costs the same. Okay? That would be true even if even there was a location-specific cost. And what's the difficulty here? Fundamentally, we discretize the state space finely, but we do not discretize finely enough. This discretization of the state space is not fine. We're using 4 discretization points at every four possible controls, whereas the space of controls is infinite. So we don't do a fine enough discretization in the control space. We need to discretize finely both the state space and the control space. On the other hand, if we have a quantity, as I mentioned earlier, the control space is finite, so this type of difficulty does not arise. However, it does arise problems with continuous control space. Okay. So it seems that the scheme with representative states is powerful, but it's not powerful enough. There are some difficulties, and the main difficulty is that it may not be easy to find a set of representative states and corresponding piecewise constant or linear functions that approximate well enough J star. And you may need too many representative states to do an adequate approximation. And that can be a problem for a high dimensional situation and so on. On the other hand, there's a variation of the aggregation idea involving representative features instead of representative states. In other words, you discretize the space of features and you form the sets within which you keep the approximation constant by using sets, a partition that involves states with similar features and then for similar costs. It's what I was talking about earlier. You use a neural network to design features for you, and then you discretize the feature space. And we aim for an aggregate problem where the states are representative features. That's a much more complicated architecture, but it's also more flexible and more broadly applicable. And okay, so I'm going to refer you to the class notes. I can't go into details on that. There's a lot of literature that you can explore. So that's all I have to say about aggregation. Are there any other questions? Okay. So we have reached the end of the last lecture for this course. And I want to close it with some generalities. First, some words of caution, just in case you've heard the rosy assessments of reinforcement learning. There are challenging implementation issues all over the place, particularly when offline training is involved, and there are no foolproof methods. Some methods work for some problems, some methods don't work at all, any problems, but they're still proposed in the literature. When it comes to architectures involving features, then you need to have domain-specific knowledge. Select good features, you need to understand your problem. When you have on the other hand, neural network approximations, they may be harder to train, And the training algorithms are not as reliable as you might think by reading the literature. Okay, I mentioned this earlier, and it's very true. Moreover, approximate policy iteration and approximation in policy space do not deal well with online replanning. On the other hand, approximation in value space does and involves a Newton step. In addition to dealing well with a changing model. That means that you have to take into account the changing costs and the changing transition probabilities as the parameters of the problem change. Suppose that you have implemented a scheme and you obtain some test results out of it. How do you know that you have succeeded? You have nothing to compare it against. You don't know the optimal solution. You just get an approximate solution, but how good is it? And I have some personal experience about that, okay? Sort of indicative. Back 25 years ago or so, an interesting test problem was Tetris. It was a nice benchmark to work with. It was sufficiently challenging, sufficiently well understood, and had the two colleagues and friends, John Sicklus and Ben Van Roy. They constructed a feature-based architecture involving 3 features, okay, for Tetris. Tetris, of course, has a zillion states, but they introduced 3 features. You know, like the height of the wall, the number of holes in the wall, and the standard, the constant offset feature. And they trained an architecture that with approximation value space score on the average 32 points per game. And then I had a student in my class who introduced a 22 feature architecture, which I think I've discussed in the previous lecture. And then we used a special method for training that architecture. And all of a sudden, from 32 points per game, we got into approximate policy iteration, 500, 1,000, 1,500, 22,000. Now we got it up to 3,000 points or 3,500 points in that neighborhood. So we thought that was a great success, from 32 to thousands. And then there were other people that followed with other methods, different methods than ours, but the same architecture, the same 22 features. And then they raised the scores to 4,000, 5,000, and we were very proud of our success. They were also proud of their success, and we thought we were doing well. However, like 15 years later, people tried some other methods, a different implementation with the same 22 features, and they got the scores to go into the hundreds of thousands, okay? So we thought we were doing good with a few thousand. They were getting a few hundreds of thousands. And how they do that is still a mystery, quite a mystery, but just different methods that were better matched to the problem. On the other hand, we did not know, we thought we were doing well, but we did not know that there were some other designs that were much, much better. We just didn't have no idea of where the optimum lied. So that gives you an example. Us and others were haggling about whose method is better, but all of our methods were lousy. And there were other methods that we did not suspect they existed and they were discovered 50 years later. That's what I mean by recognizing success or failure can be a challenge. Here's something else to keep in mind. There have been spectacular successes of reinforcement learning in game context, like chess and backgammon, but these successes have benefited from a perfectly known and stable model. Chess is a stable game. The rules don't change from one day to the next. Also involves a small number of controls, like 30, 40, okay. problems involving changing models, like an adaptive control, and involving a large number of models, like a continuous control space, are far more difficult, even though chess is considered a challenging game. There are problems out there, common problems in practice, that are far more difficult. Problems with partial state observation remain a big challenge here. Okay? There have been successes, but it's always a challenge to deal with a POM-DP type of problem. Okay, so on the positive side, approximation in value space and rollout are relatively simple and reliable. They tend to work almost every time. So my advice to you, when faced with a new problem, is the first thing you want to try is approximation in value space with simple post-function approximations, and also rollout. After you do that, then you may want to become more ambitious and try some other methods involving offline training, like, for example, neural network type of methods in conjunction with policy iteration. Don't be discouraged if you fail, okay? It has happened to many people, but keep on trying. Maybe you'll get lucky at some point for your problem, okay? You may have a method that may not work on other problems, but may work on your problem with tuning and hacking and so on. If you fail completely, despite your efforts, go back to rollout, because it will seldom fail you. All of the methods that we have discussed can benefit from parallel computation. Simulation is very well suited for parallel computation. Similarly, you can compute in parallel Q factors. And that's a source of hope to deal with the massive computational problems involved in this area. There is a silver lining here. The kind of problems that we can consider with reinforcement learning methodology cannot be addressed with any other methodology. There are problems of unimaginable difficulty, unimaginable even a few years ago. Therefore, we're aiming to solve big problems, important problems, and there's a good chance that something will work with skill and luck. So on the whole, there is an exciting and long journey ahead with applications of reinforcement learning in a great variety of different fields. There's a lot of interesting theoretical work to be done, a lot of interesting implementation work to be done. So these are general comments on the course, the content of the course. And okay, some words of wisdom. You know that all professors like to give words of wisdom to the younger generation. Well, I have no words of wisdom, but there are some quotations that I'd like to give you, like the words of wisdom of other people. The first one is that the book of the universe is written in the language of mathematics. Okay, so why is it that we can understand the world around us with mathematics? It's a big mystery, one of the big mysteries. Why is that? Why is it mathematics that allows us to get deeply into something that's very real, the real world around us? So it's also an opportunity to use mathematics in creative ways to understand what's happening around us in engineering, physics, social sciences. Don't forget that no matter what kind of methods we have, no matter what computer we use, what tricks we use, mathematics is at the bottom of everything, okay? It's the foundation of everything. Okay, so here's another quotation that involves the word learning. Learning without thought is labor lost. Thought without learning is perilous. At the teachings of Confucius. Now, you have to understand this quotation in the context of the language of Confucius' day, where learning was sort of synonymous to obtaining knowledge, and thought had to do with the ideas on how to do things. So to translate properly this quotation, you have to think of it like, okay, getting knowledge without ideas what to do with it is labor lost. Having ideas without having the proper knowledge to implement them is perilous. Okay. A quotation from Plato about learning from experience. Many arts have been discovered through practice. Empirically, experience makes our life proceed deliberately, but inexperience unpredictable. Plato attributes this to Socrates. Socrates did not write anything. Plato wrote for him. And it's appropriate for our subject because we can understand what's happening in reinforcement learning very often empirically, by looking at the numbers, by looking at the results, looking at how different methods work. The methods are difficult to understand, the problems are very complicated, so practice and testing is important in this field. Deng Xiaoping, white cat or black cat is a good cat if it catches mice. A lot of what's involved in our field is what works, okay? If it works, it's good. If it doesn't work, it's bad. It may be theoretically beautiful, but if it doesn't work, it's not good, okay? So the proof is in the actual practice. And so these are old quotations. Let me give you a couple of recent ones. Machine learning is the new electricity. Andrew Ng is a professor at Stanford. He is or was a professor, I'm not sure. Says that electricity has changed how the world is operated, and it's found application transform many fields, and artificial intelligence is poised to have a similar impact. There's no question artificial intelligence is going to have a great impact. I thought that this quotation was a bit optimistic. But after seeing ChatGPT and the hopes that it has raised, I tend to think that Andrew Ng had it right to a great extent. So this is an optimistic quotation. There's another one that's more tempered assessment of artificial intelligence and machine learning. Machine learning is the new alchemy. Ali Rahimi and Ben Recht. These were students of mine in my class at MIT a long time ago. They're now quite prominent in machine learning. And what they say is that we do not know why some algorithms work and others do not, nor do we have rigorous criteria for choosing one architecture over another. Like in alchemy, you mix ingredients and something happens. Some things are interesting, some things are not so interesting. But even if they're interesting, you can't understand why it happened, what's involved, what are the mechanisms that make it interesting or effective. So it's the same thing often with reinforcement learning. You may put a lot of algorithmic ingredients together, and sometimes you have success, sometimes not. But just why you're having success or why you have failure is often hard to understand, because the algorithms are complicated, the networks are fake, so on and so forth. So a lot needs to be done in this area of understanding and transforming the alchemy more into a science. There's a lot to consider, a lot to think about, but our course is over now. And I thank you for your attendance. I should correct, our course is not over. You still have your term papers and projects to submit and discuss with the class, and wish you good luck with those.